Today we're going to talk about diode electronics. And I really recommend you read the SparkFun website about diodes and the Maker tutorials on diodes. They're written very cleanly, and the only thing that I'm adding is showing you LTspice and a little bit of engineering on top of it. But I really would read through those first before looking at my slides. So let's just review. Ideal diodes allow an infinite current to pass in one direction and zero current to pass in another. The forward region of the diode has zero resistance, current flows easily, and in the reverse region the diode has infinite resistance, current can't flow at all. So in the forward region, zero resistance means it would be a short, like you just put a wire from the anode to the cathode. And in the reverse direction, it would be as if you broke the wire between the anode and the cathode. So just to summarize again, forward bias on a diode, the anode voltage is greater than the cathode voltage. Reverse, the anode voltage is less than the cathode voltage. And I can see a little error there, and I'm sure you can figure that out. I'll fix it in the notes. So here's an example. The anode is at 1 volt, the cathode is at 0 volts, the anode is greater than the cathode, the diode is in the forward region, current should flow. So if we look at this battery, here's my definition of ground, and I'm going up 1 volt. So the anode is at 1, the cathode is at ground 0. This is a higher potential than that, and current's going to flow. In this case, the anode is at minus 1 volt. Because here's my definition of ground, and I'm going minus 1 volt up here. So in fact, this is reverse biased, and current won't flow. And in this case, just slightly different, the anode is at 0 volts because I have put ground here, and the cathode is at minus 1 volt. Yes, it says 1 volt here, but I'm referencing it from ground, and so it turns out to be minus 1 volt. Well, if this is at 0 and this is at minus 1, this is a lower potential than that, and it's actually forward biased. It might not seem very intuitive, but if you're confused, go reread these notes. And if you still don't believe it, you can download this file and run it and explore it for yourself. All right. And just to round it out, we've tied the anode to ground, and we have a -1 battery voltage, but I'm going -1 from ground, and so in fact this is at a higher potential than that, and it's reverse bias. So the cathode is actually at a higher potential than the anode because of the definition of these voltage sources. Okay. Now let's put it in a real world example. We have a battery, 5 volts. We have a resistance, 1 kilo ohm, and a diode. This is a specific diode. So let's assume an ideal diode. I don't know what the voltage is here, but if this is 5 volts, then node 1 will be at 5 volts. And that's pretty much guaranteeing that this node will be at a higher potential than this node. So it should be forward biased. So if it's forward biased, there won't be any voltage drop across it, and there won't be any resistance. So I should just get 5 volts divided by 1 kilo ohm and get 5 milliamps. Well, let's simulate it and see what we really get. Okay. In this case, though, before we do that, we'll put in a -5 volt. So that will mean that node 1 is at -5 volts, 2 will be negative, and so it'll actually be reverse biased, and so no current should flow. Now we'll simulate it. Well, it turns out that across this diode, in the ideal diode, there was no voltage drop, but notice V2 is 0.65. What happened there? Well, we'll talk about that a little bit later. Interestingly enough, the current is 4.3 milliamps, not 5 like we had said. Now, this is a 14% error. And the reason why is that diodes do have a voltage drop before they really turn on. And you can call it V forward or V diode forward voltage drop, but it does exist. And you can look this up at a data sheet. Thing is that I've just run the simulation, and you can see that we're at 0.65 volts. So all I have to do is modify Ohm's law. V1 minus V2 divided by this resistance will give me the total current through in the circuit, because all these elements are in series, right? So when I do that, I actually get 4.35 milliamps, which is really close to what I had calculated. Now you might ask yourself, hey, why use this ideal diode model at all? Well, for just assuming that it has zero resistance forward and infinite resistance in the reverse, I was able to get an answer very quickly that was within 14%. Now what about reverse bias? Well, I put in a minus 5 volts. This should be an open circuit. The current should read 0, right? But it does read minus 2.52 nanoamps. And that's because there is a leakage through there. And in this case, though, for most cases, 2.52 nanoamps can be considered almost 0 amps. Now, this diode does have an equation, and you have positive, negative. So V diode is measured from positive to negative, and this is the saturation current, Boltzmann's constant, temperature, charge of electronic charge, ideality factor, and this equation is nonlinear. Okay, and we're actually going to make use of that later. But this is really what goes on. Thing is in electronics, we don't actually have to worry many times about the full-blown diode equation. Okay, what we need is a data sheet, and rather than use this equation, it'll give us a pair, a current and a voltage, right? So basically, it's one point on a curve where this diode and current and that diode voltage will be true. Okay, and you can look it right up on the data sheet, and here's the link. All right, well, let's see what we get. So if the forward voltage is 1 volt and the forward current is 10 milliamps, all I have to, and I want to have 10 milliamps in this circuit, all I have to do is solve for R1. Well, I can rearrange this equation to solve for R1, V1 minus VF, 5 volts minus 1 volt, divided by the forward current, 10 milliamps, gives me 400 ohms. So then I run it. And what do I get? I get V2 of 0.697 volts. So this V2 would be VF. They're supposed to be the same. Okay, I could easily put a label here of VF. Now the current is good. It's very close to 10 milliamps, but the voltage is certainly not 1 volt. In order to get a voltage drop of 1 volt, in fact, I had to change this resistance down to 10 ohms, but what happened? The current went up to 300 milliamps. So, unfortunately, the data sheet, this pair is wrong. And anybody familiar with silicon diodes knows that 10 milliamps in general is going to be 0.65 or 0.7 volts. Okay, it can happen. So sometimes you need to verify. But however, let's look a little more detailed at that data sheet. Well, there's actually a curve that shows forward current and forward voltage. And if you look right here at 10 and drop it down, hey, it is about 0.65, 0.7. So, in fact, even though the data sheet had this 1 point wrong, the curve was good. And when we simulated it, we got very accurate results. Now, as you know, we have resistor tolerances. And so what happens if R1 has a tolerance of 10%? Well, this can get really tricky with a nonlinear equation. But let's go back and see if we can simplify it. So if I just assume VF is going to be 0.7 volts, meaning it won't change that much. And how can I say that? Well, look, this is an exponential relationship. The voltage changing a little bit causes a huge change in the current. But on the other hand, a huge change in the current causes a tiny change in the voltage. So this is going to be a good assumption. So what's the largest R1 can be at 10%? 440 ohms. I put it into I solve for I forward of what I think it should be, and I get 9.77 milliamps. And when I run it in LTspice with the proper resistance value, yeah, I get almost the same, 9.78 milliamps. And yes, the forward diode voltage changed, but it didn't change that much. Again, when I find out what the maximum current can be, again, there's a typo there. I get 11.794 milliamps, and it matches pretty well. So the thing is VF not changing. It's actually a pretty good approximation.